For 7S turbine that we are going to consider here, the dimensions are given here and they are taken from the Blackwell et al. And you can see the report. Wind tunnel performance data for 2 and 3 bucket 7S rotors. And if you go through this all information, you can see the speed is 7 and 14 meter per second, and rotor diameter is 1 meter, not exactly 1 meter, and the bucket overlap is 0.1 to the 0.1 meters. Okay, so let's go to the details, more details here. Okay, here is the picture that I am like I was showing you in the previous slides, and the data that we are using is given here. Okay, so test number, it's figure number 16, and the run number is 2122, and configuration number is 9. And the gap S by D ratio or overlap ratio is 0.15. Height is 1.0 meters. We are not taking the height right now because it's a 2D case. And velocity we are going to consider is the 7 meter per second, and the area is a 0.979273. It means that the area for 7S turbine is a diameter into height. So if the height is 1 meter, it means the diameter would be the 0.9273 meters, or 9 to 7.3 millimeters. And the radius would be definitely the half value, and Reynolds number is given here. And similarly, for this turbine, they have also provided the bucket diameter, and they have emphasized that the bucket diameter is 0.5 meters, that you can see here. So the bucket has a radius of 0.25 meters or 0.5 meters diameter. Okay. So same data is given here. The rotor diameter, that is overall diameter of 7S turbine, is 927.3 millimeters. Height is 1 meter. We are not using it, and so it means that aspect ratio, that is H by D, is a 1.078. Bucket or blade diameter, semicircular blades, they have the diameter of 0.5 meters or 500 millimeters. And overlap or the gap is the 75 millimeter, that is coming from the of the overlap ratio S by D of 0.15. So you can either go from this way or from, but the best way would be that you should define the overlap ratio and put the value of diameter and find out the overlap value or the distance. And the blade thickness, if you take into consideration the diameter of the this whole turbine, that is 927.3, and gap of 75 millimeters, bucket diameter of 500 millimeter, then the thickness of the blades would be the 1.15 millimeters, and incoming velocity is 7 meter per second, and there are no end plates. So now to start the project, I am going to open the workbench, and from here I am going to put the fluid flow fluent, and it contains the multiple options for geometry, mesh, and fluent setup and solution. And if required, you can also go to CFD post. So first of all, double click on the geometry, and it should open your design modeler. If not, then you have to go to the tools menu, and from there you have to set the default geometer editor, or you can right click here and you can open the geometry in the design modeler. So there are three options will appear. I will show you. So if you right click here, you can either open the design modeler or space claim or even the discovery. Okay, so first we are going to draw the rotor domain, or first the rotor blades and then the domains, the inner domain, the wake domain, and the outer fixed domain that is going to provide you the boundary conditions. Okay, so we are going to take the units as millimeters, and zoom your geometry, the scale here as per requirement. So our diameter is 927.3 millimeters. So take the scale of around 1000 and go to sketching mode, and from here click on the circle and click on the center point, and you should see the symbol P. Okay, and draw one circle. Okay, now for the dimensions, click on the circle here, and the diameter of the outer circle of the 7S turbine is 927.3 millimeters. Okay, now I'm going to draw. Now there are the if I give you some idea here. So here you can see that we have the one blade that's returning and one blade that is advancing. So if the wind is coming from there, then you can imagine that the direction of rotation would be the anti-clockwise. If the blades were were flipped there, the direction of rotation would be the clockwise. Okay, so right now it's the anti-clockwise, and same thing we are going to implement. Okay, so here now what we have to do is that we have to make a one circle for the bucket. So where this point should be placed, if I drawing a circle here somewhere, this will be the second blade. Okay, the first blade, and the first blade is actually a returning blade. If you want to have the anti-clockwise, this should be like on the top side, and if it's like advancing blade, then it should be on the bottom side. So let's try from here this way. Okay, so now the first question is that now this is going to be the my returning blade, and the blade on this side will be the advancing blade. Okay, if you rotate the geometry slightly, you will understand very well. And here I would put the dimensions about the center of the circle, and this center should be placed where? This center should be placed now, let me tell you. See, from the definition of the from the spacing, that is the 75 millimeter, and this is coming from the overlap ratio of the 0.15. Now 75 means that the half would be the, so this is going to be the 37.